All right, welcome everyone. We're delighted to have Professor Azita Emami here for our colloquium today. Azita is a professor of electrical and mechanical engineering at Caltech, as well as a Heritage Medical Research Institute investigator. She's also served as the equivalent of the chair of the electrical engineering department. She got her MS and PhD degrees in electrical engineering from Stanford in '99 and 2004, and did her undergraduate degree from Sharif University of Technology, which is renowned for this undergraduate and circuits program in particular. From 2004 to 2006, she was with IBM TJ Watson before eventually moving over to Caltech in 2007. Her current research interests include integrated circuits and systems, integrated photonics, as well as wearable and implantable devices for neural recording and stimulation, sensing, and drug delivery. She's currently the associate editor for the IEEE Journal of Solid State Circuits, which is the premier journal and publication in our field, and was an IEEE SSCS distinguished lecturer in 2018 and 2019. So without further ado, Azita, please take it away.
Thank you so much. Thank you all for joining us today and for having me. So today I'm going to talk about some of our research efforts related to biomedical devices, in particular implantable wireless devices. And in my group over the past 10 years or so, we have worked on a variety of such devices. And I'm just showing here some examples. In the past, we have worked on intraocular pressure sensors that are wireless for patients who have glaucoma. Here on the top right side, I'm showing an injectable glucose sensor that is completely wireless, batteryless. It has RF energy harvesting and can be injected right under the skin. And an external reader can power it up and read the glucose level out for patients who have diabetes and they have to prick their fingers every day. So we've been also working on technologies to be able to localize these devices, this kind of devices inside the body. This is another example here in the middle. We call these atoms, which allows us high precision localization inside the body. And that's one of the projects that today I will focus on. And then finally, we've been working on neural interfaces over the past 3-4 years. First, we worked on seizure detection and more recently in brain-machine interfaces. And that's another topic that I will cover towards the end of my talk if I have time. So let me start with our efforts related to device localization inside the body. So imagine if one day we have sensors that travel inside the body trying to measure things or even deliver drugs inside the body. It's very important to know where they are. And, but even in today's applications, when we have capsules or smart pills going into GI tract, it's important again to know the location of these devices. Another area that localization of micro devices inside the body would be very important is related to high precision surgeries, navigation during these kind of surgeries, robotic surgeries, minimally invasive laparoscopic surgeries. In all these applications, navigation and localization would be very important. In some of them, sub-millimeter accuracy would be greatly beneficial. So that's something that my group has been focusing on. And the problem with current localization methods are a few. And there are several approaches. One would be very similar to how GPS triangulation works with using RF signals and then looking at the strengths of the received signal or time of flight or time difference between arrivals or angles of arrivals So these techniques, while they work quite well for a system like GPS inside the body, they fail, especially if we want to go deep inside the body, or if we want very high level of resolution. Because RF signals at higher frequency, they experience a lot of attenuation, multipath, and also highly depend on the body composition, whether the person has more muscle or more fat in their body. So there are also ultrasound-based approaches. Again, they have poor performance for bones, airs, and gases inside the body. And of course, optical-based that are used in several types of surgeries. There are also, they have their own limitation in terms of penetration inside the tissues. So we've been looking at this from a different angle, relatively different angle. And our approach loosely is inspired by how MRI works. And as you know, MRI gives the highest level of resolution for locating nuclear spins inside the body. And they can distinguish location with better than or close to 100 micron of resolution. So I'm sure many of you are familiar with the principles of MRI. Just very quickly, I will review it. MRI, of course, relies on a very high magnetic field to align the nuclear spins. You can think about them as hydrogen atoms that are being aligned. And then there is a gradient, magnetic field gradient, and an RF excitation. So after the RF excitation is removed, depending on the location, because there is a gradient in the magnetic field, different atoms oscillate or do the precession at different rates. And this is called the Larmor frequency. And therefore, we can look at these frequencies at different, and then map it back to location. So in our project, we also call these devices atoms, because we are building these micro devices that behave quite similar to real atoms or nuclear spins inside the body. So the idea here is that to have these micro devices or chips that, depending on the location that they are inside the body, they will oscillate at a different frequency. And the nice thing about this approach is that we don't need the very high strong field of the MRI, which makes MRI systems extremely expensive. So we call these devices also atoms, standing for addressable transmitters operated as magnetic spins. So we basically not only can locate them, we can also communicate with them, hopefully. So let me show this in a little bit more of detail. So the idea here is, again, to create a magnetic field with a known and controlled, well-controlled gradient. And then we have the tiny chips inside the body. And depending on their location, they will send a tiny, tiny signal at a specific frequency. And then we shift that frequency based on location by measuring the magnetic field that each chip is experiencing. So we tried to kind of mimic different phases that MRI systems have in our system. Basically, at the first phase, which call this the magnetic phase, the chips basically measure the magnetic field. And then we have the second phase, the excitation phase, where we actually send a reference RF frequency at F0 to the chips, so that all the chips basically lock to the same frequency. So that's kind of the difference that you see here. We have a PLL on chip, as I will show, and all of them will lock to this frequency. And the nice thing about this approach is that you can have many number of chips, and as long as you can differentiate the frequencies of oscillation, you can identify one from the other. And then we have the transmission phase. This is when we basically allow the on-chip oscillators to oscillate at different frequencies based on what we have measured during the first phase, which is the magnetic phase. And we shift the oscillation frequency, and therefore we encode location into frequency. So as you can imagine, so there, the principle is actually quite simple. So we have to generate a monotonic, well-known magnetic field with a known gradient. And then our chips will translate the measured magnetic field to a delta F with this factor of gamma. And then we have to look at the profile of the magnetic field and look at the inverse of that function to map it into location. And the resolution will depend, of course, on the noise performance of the magnetic field as a magnetic sensor to measure the magnetic field. There is a noise and offset associated with it. And then there is a phase noise associated with the frequency generation on chip and transmission of that frequency. The nice thing is that the frequency doesn't change as the wave travels inside the body. So we have looked at all these noise analysis in our publications, the noise of the sensor, the phase noise of the PLL, and how much averaging. By averaging, basically, we enhance the performance and the resolution of localization. So this is the chip architecture. This is the first chip that we had. It has an on-chip magnetic sensor that I will talk about it. It's a MagFET. Then we have trans-impedance amplifiers and low noise amplifiers with chopping to reduce the low frequency noise. And then there is an on-chip antenna that receives the external RF frequency. And this antenna acts two ways, first as a receiver and then later as a transmitter. And we receive the RF signal. There is a phase lock loop that locks to this RF signal. And then after we measure the magnetic field, we open the phase lock loop, we shift the frequency of oscillator, and through a power amplifier, we send the signal out. So let me talk a little bit about the magnetic sensor. So our goal has been to include everything on a single chip. And so this is a split drain magnetic sensor in CMOS technology. So that's at the heart of the design. And there is a direct trade-off between how much power consumption, how much current you send into the device. So as you can see, we are biasing the device. Just let me very quickly explain what it is first. So this is like a MOS transistor where we split the drain of the transistor in two sections. So, and we bias it with a current I of B. So if you have a magnetic field perpendicular to the device, then because of the Hall effect, we get two different currents in the two drains, ID1 and ID2. So if we read this out and digitize it, then we have a sense of what is the value of the magnetic field at a given location. So, so there is a lot of optimization that needs to be done to trade off between the sensitivity of this MagFET and how we bias it, how we size it, the noise performance of it, and so on. So we put a lot of effort using the technology parameters that we could get to first optimize this device before fabrication. So let me also talk a little bit about the phase lock loop, which is again very important. After we measure the magnetic field and we lock the phase lock loop to the incoming RF signal, so here is the lock phase, we have to open the phase lock loop keep the frequency, and then shift the frequency accordingly based on what we measured, based on the measured magnetic field, which gives us delta F. So as you can, if you are circuit designers, you know that this is quite difficult because, and as I will show, basically you want to lock and then you want to open the loop without changing the frequency. So you want to reliably keep that frequency and then again reliably shift it. And you have to do this very quickly before you have too much drift in your oscillator. So for doing this, there are a lot of details again in the PLL design that I'm not going to go through it, but we did a lot of work into this by designing the PLL using a low KVCO, the voltage controlled oscillator, to make it less sensitive to variation of V control. We also sample the V control in a way to make sure that we keep it correctly and we avoid overcorrection of the loop as we are opening the loop. So this shows a very simplified block diagram of the PLL where it locks. There are 3 phases. It has a calibration phase, then it's a normal operation of locking, and then we sample the V control into capacitors, relatively larger capacitors than the loop capacitors. And then we basically connected, we open the loop, we shift the frequency, and we perform transmission. So basically this shows some of the measured results of the PLL, where we have wireless locking via an RF pulse. As you can see, but the nice thing is that we need to, we do everything in millisecond regime. So we showed that actually after the initial lock, so this is the initial free running frequency of the oscillator. This is after the RF signal comes in, we lock. Momentarily there is a shift, but we bring it back because of the correction in the loop. And then the oscillation stays almost reliably constant for a few milliseconds that we need. If we wait longer, of course, the frequency starts drifting. So this is also a measured result that shows what happens if we have different magnetic field at different locations. So these are the 3 different magnetic fields for the PLL. First, the PLL locks. Then we shift the frequency to 3 different values based on the measured magnetic field at 3 different locations. And this is the chip. It has 2 sets of coil. One is for power delivery. The other one is for RF coil that I mentioned, and PLL, LNA, TIA, magnetic sensor, and all the required building blocks. So again, this shows how we receive the signal externally wirelessly at different frequencies as the oscillator is being shifted. And it shows that we can reliably separate frequencies to measure location. So we first did a 1D localization. In the very first design, we basically just put a permanent magnet in one location, and then we moved the chip on x-axis to show whether we can do localization. So as you can see again, at 3 different locations of x1, x2, x3, we receive different frequencies. This is the power spectral density of the received signal at 3 different frequencies. Then we, based on the measured magnetic field that we do it with a precise the commercial magnetic sensor, we create a map of the magnetic profile, and then we go from frequency to location. So this shows the performance. As you can see, we can get sub-millimeter accuracy. This is the error sigma of the error in localization, which is consistently below 130 micrometers for this 1D experiment. So to do 2D experiment, again, in this very first version, we put first one magnetic sensor, we do a measurement, we remove this permanent magnet, we put another permanent magnet, and then at the other corner, and then we do the 2D measurement. And I have to say that in this particular design, because we had just the 2D magnetic sensor on chip, we performed 2D localization, but I will talk about 3D localization very soon. So this shows the actual measurement as we put the two magnets in two corners. And again, we showed that we can perform very high resolution localization. Here is when we move the chip to Wright California Institute of Technology, CIT, and we get very high resolution of, again, below 100 micrometer of accuracy, error. So we also did in vivo localization in a crude way. We had the chip in a mice, and we moved it with a shaft. Again, this was an anesthetized mouse. And of course, because in this case, in vivo, our resolution or accuracy dropped a little bit, but still we showed 2D localization in vivo that was better than 0.5 millimeter. Again, this is much better than multi-millimeter accuracies that RF triangulations achieve. So this was published a few years ago and got the cover of Nature Biomedical Engineering. But the nice thing that happened after we published that is that we got contacted by a number of physicians and people in the medical field with potential applications of this device. And we realized initially we were thinking this would be used for smart pills, but then later we realized that it can have a lot of different applications. So, so in particular, we focused on two applications. One was the smart pills, and the other one was high precision surgery. So from industry, people contacted us regarding, in particular, about orthopedic surgeries that require a lot of alignment, very precise alignment for different procedures. And usually these procedures involve, because of difficulty of alignment, require multiple x-rays as they do the surgery. It highly depends on the expertise of the surgeon. Some surgeons do these things very quickly. Some of them, it takes for them hours to do it. So one of the areas that would be interesting is, for instance, how to fix implants inside the bones, because again, you don't have any visual access, and you want to, for instance, lock the bones or align them for hip replacement or knee replacement. So the idea here would be to tag the nails or the implants or even the bones, because we realize that actually orthopedic surgeons all the time, they put extra like screws different places inside the bones and so on. So we can actually use our atoms chips as tags in different places, and also put them also on the surgical tools to be able to localize things with very high precision. So one of the applications that we focused on, because again, the implant companies suggested that these are very difficult surgeries, was the IM nailing, which is the intramedullary nail. Again, you have, if they're putting an implant, these are long nails that they put inside the bone. And then at the end of the implant, they need to lock it using a screw. And again, there is no visual access to where the hole is with respect to the screw. So imagine if we add one of our tiny chips next to the hole and then another one on the surgical tool, then on a monitor, we can show to the surgeon where they are with respect to each other. And then we completely eliminate harmful x-rays and we expedite the surgery. So in this case, we would want nothing to block the surgeon. They don't want anything added to the environment. So the idea here is to create a field generator mat that can be put right under the bed where the surgery is happening to create the magnetic field that we want, and then perform the measurements that I described before. So since then, we have made a lot of progress actually to design also the magnetic field gradient coils instead of having permanent magnets that we had at that very early design. So we generate X, Y, Z magnetic fields with almost linear gradient in a very large, relatively large field of view in XYZ direction by having 3 sets of coils as I'm showing. So the first, the red one creates the gradient in X direction, the blue one creates the gradient in Y, and Z creates the Z. And basically a lot of simulation and engineering went into designing these coils to be able to generate reliable and very high, very well-known gradient in these magnetic fields that are being generated. So then we put all these 3 layers on top of each other and we turn them on and off in consequence. So first we turn the X coil, we measure the X dimension, then we measure the Y, and we keep the Z coil on all the time. Again, I'm not going through the details of it. By keeping the Z coil on all the time, it allows us to bring the magnetic field level up and avoid having plus minus magnetic fields. So it makes the measurement better, easier, and creates a more monotonic field and increases also the field of view. And then we quickly do the measurement in each phase. Right now, we are limited by how fast we can ramp up the currents in these coils, but they can definitely improve in the future. So these are the actual coils that we had in the lab. Again, the same XYZ. The first one that I showed you was simulation. These are the actual measurements of the field that are generated by these 3 sets of coils, and then as I mentioned, we put them on top of each other. So for the orthopedic surgery, we actually designed a new CMOS chip that is completely wireless with wireless power, wireless data, and also it has an RF wake up because we don't want to have any batteries for these devices if we end up leaving them inside the implant, inside the nail, orthopedic nail for the patients. So in this quick, basically prototype that we had, this time we used the commercial 3D magnetic sensor as we are designing our own on-chip magnetic sensor that will finish soon. But in this case, we used a commercial magnetic sensor to make sure that we don't have. So we did a lot of optimization to reduce the power consumption and to wake up the device only when we want and communicate with sensor in an efficient way, because wireless power delivery, as you may know, is not very easy inside the body. And so we put a lot of effort into the power management circuitries and making the system very low power. So this was fabricated in a 65 nanometer CMOS technology. As I mentioned, it has bidirectional data telemetry, I2C communication with the magnetic sensor. This was actually presented at ISSCC 2020 back in February, which was maybe the last conference that we all attended right before the lockdown. So, so then we in the lab, these are the actual coils. We have this tank of saline. So the black thing is the tank of saline, and the chip is on a platform that can be moved around, and the wireless communication and power delivery also is under this tank of saline. And this is the tiny board that includes our CMOS chip, the magnetic sensor, which is the main reason that is a little bit bigger than what we want. But as I said, we have a new version that has the magnetic sensor on a chip. And then we have this coil that goes around the PCB board for wireless power and data. So this was successful in terms of localization. We did XYZ localization. And of course, because of the magnetic sensors noise, random noise, we showed that if we do enough measurements, as soon as we go beyond 20 measurements, resolution improves to better than 100 micron, which is state of the art in terms of localization. So we perform the same type of XYZ measurements and averaging to get very high resolution localization. So this is shown for 3 different locations, Y1, Y2, Y3. Usually we get the best localization results right in the middle of the field of view where we have the highest gradient. And averaging, of course, helps a lot. So here is the summary of performance of this chip. It does 3D localization with better than 100 micron accuracy, and is fully wireless with a very good field of view. So, so this was the first quick prototype that we built for navigation during surgery. But as I mentioned, we are working on the next generation, which will help for hip and knee alignment. And hopefully we'll make a lot of these surgeries faster, safer, and more accurate. So I can actually stop for a second here if any of you have a question before I switch gear to the next topic. I can answer some quick questions right now, and then I move to the next topic. I guess you guys can raise your hand. I see one here. Let me, Blake. Let me unmute. Oh, hold on. I'm not sure.
Hello, let me see.
Yes, Blake, please go ahead.
Yeah, he should be unmuted.
I
Yes,
see
Blake,
that
please go ahead.
Yes.
Hi, Blake, are you there?
So maybe he has difficulty. I see that his audio is not connected. So maybe anybody else? Is there any question regarding this first project related to localization?
Hello, can I ask a question? You heard me?
Sure, yes.
Hey, this is great work. I have a question. So in the second version, you switched to the digital backscatter data modulation instead of the PLL based, right?
Yes, yes. Oh, I forgot to mention that, yes. Because in the second case, we are not dealing with too many devices. The first case was envisioned if we have many of devices inside the body, especially for application for GI tract. We usually want to have many of them travel at the same time inside the GI tract. But in this case, because the numbers are limited, we realized that we can make it much simpler by simply just sending the magnetic field out.
I see, thanks. And what was the trade-off in the power, like the power consumption between these two methods?
That's a great question. So Of course, the first, if we don't do frequency encoding, we save power on the chip. But overall, the second version, unfortunately, had a little bit higher power because we used an external magnetic sensor. So the power is really dominated by this commercial magnetic sensor. And we believe that we can reduce this by a factor of 10 in our next generation of on-chip magnetic sensor.
I see, thank you.
So it looks like Blake asked this question via text. How sensitive is the measurement to the presence of metal objects which could distort the field?
That's a great question. So, of course, if we have ferromagnetic objects close by, it will distort the magnetic field. But fortunately, what I didn't show is that we actually tested the system with actual implant, which is usually titanium. So titanium is not a magnetic material. And fortunately, it did not affect our magnetic field at all. Also, surgical tools, a lot of them are not magnetically active or ferromagnetic, and therefore they do not distort the magnetic field. However, our next step, we actually just right before the lockdown happened, we were scheduled to go to an actual OR and test it in an environment that includes everything. So that's a great question, and that's something that we still need to fully test it, but we have tested with surgical tools and the titanium implant itself, and we haven't seen distortion of the magnetic field. But the titanium rod actually causes some degradation of wireless power delivery that we had to actually, when we put the chip into the implant, we actually have a small cavity under the chip to avoid eddy currents in the titanium implant that would degrade the wireless power delivery. Great question. So maybe I'll move on, and then at the end of the talk, if you have questions about this section of my talk, feel free to ask. So I think I still have maybe another 15 minutes, so I will move to the next section of my talk. But before that, I would like to, of course, acknowledge all the students who were part of this project. Manuel Monge, he is actually now a professor at USC, and Professor Mikel Shapiro at Caltech has been our collaborator, who is an expert in imaging and MRI systems. So now I would like to also talk to you a little bit about our research projects related to neural interfaces. As I briefly mentioned at the beginning, we've been interested in neural interfaces, especially trying to move towards miniaturized implantable devices. First, we worked on epilepsy because, as you know, there are a lot of data available for epilepsy. And that kind of led us to our newer efforts related to motor prosthetics and brain-machine interfaces. And so today I will talk about our collaborations with Professor Richard Anderson at Caltech, who is a pioneer of brain-machine interfaces, in particular looking at certain regions of the brain, AIP, anterior intraparietal, parietal region of the brain that associates with grasping and hand movement. So in this case, as this is a patient that has been working with Professor Anderson for many years. So we are one of the few groups across the globe who have been able to work with human subjects. So there are penetrating electrodes inside the brain at these 3 different regions of the brain, SMG, PMV, and S1. So each electrode array is a Utah array with, so overall we have hundreds of electrodes and a huge amount of data to basically read the data out and then predict the intention of the patient in terms of moving his hand. And usually we train the patient with these center out tasks on the screen with the cursor in the middle of the screen and the patient imagining or trying to move the cursor from the middle point to the points outside, to 8 different points outside of the center. So the patient, this has been actually going on for a few years, and it's been quite impressive how patients actually can use this kind of brain-machine interfaces to move a cursor across the screen. So as you can see, this is a tetraplegic patient that by thinking is moving a robotic arm that is pointing to this red square on the screen. A few groups have been working on this kind of systems, but as you can see, the system is very bulky. The arrays are inside, and there are amplifiers and very big wires coming out. It goes to a BlackRock module, and then it goes to the computer to run the algorithms. So let me first tell you a little bit about what's going on right now, what's the common approach today in terms of reading the data out and controlling the robotic limb. So in most cases, the nice thing about these penetrating electrodes is that really give us single neuron activities. So we can do spike detection. For instance, in this case, the electrode is reading from 2 different neurons, but we can, by looking at the features of the spikes, we can actually perform clustering and separate the 2 neurons and basically create, look at the firing rate of each neuron. So in most systems, if you look at them, they actually use this firing rate as their features per electrode or per neuron. And it is done by creating beams of 50 milliseconds and usually counting the number of spikes in that beam. And in most cases, then the spike or firing rates go to a decoder for predicting the kinematics or the movement that the patient intends to have. And in most cases, a Kalman filter or a variation of Kalman filter or Wiener filter is used to predict the kinematics. But unfortunately, there are a lot of challenges remained for robust brain-machine interfaces. First of all, as you see, what we saw is completely at the clinical setting, so the patient cannot use it by himself or herself. They cannot go outside. So this is a very controlled setting with experts attending the patient and connecting to big machines. But in addition to that, there are a lot of non-stationary conditions. So what happens if you look at the activity of different electrodes or neurons? They come in, they go out. Sometimes they have more importance, some electrodes, sometimes they have less importance, sometimes they're just generating a lot of noise. And therefore, for each of these sessions, even if you have a half an hour session, you need to have a training at the beginning to adjust the parameters. So that's a big problem towards moving towards an implantable device that a patient can use in everyday life. So the other issue that patients report is the latency in the loop from the time that they're thinking by the time that a movement is happening and the correction. So you would like to have a nimble system that the patient can, based on the visual feedback, they can correct the movement. So the latency in the loop is another issue. And then there are actually a lot of misclassifications. So the patient wants to move in one direction and the cursor is moving to the opposite direction. And of course, there are noise and modeling insufficiencies and errors in the system. And of course, on top of that, for someone like me who is interested in implantable devices, the hardware complexity of the algorithms and the whole system is mind-blowing and very difficult to move towards wearable and implantable devices at this point. So, so our goal is to basically take steps towards robust and energy efficient brain-machine interfaces, to look at the system as a whole at some point, but right now we are not focusing on the front end. As you know, there are many groups who are focusing on the front end design and digitization. We've been for now focusing on the decoding part and also feature engineering. So I will talk a little bit about these two aspects of our project today. And I have to be careful about the time to leave enough time for question and answer. So we've been looking into, instead of using the Wiener filter and the Kalman filter, to use machine learning algorithms to decoding kinematics. And again, from the hardware perspective, just a reminder. So if you look at a neural network, you have the MAC units that they do multiplication, addition, and then you need a nonlinear function. But what really takes energy and increases the power consumption of a chip that does the inference is the loading of the weights. You need many number of weights in deep learning, and you need to load these weights from a memory to the system. So that's really energy hungry to move bits around. And then another thing is that you have to also have a memory of the neural data. So because what the kinematic depends on not just the neural data at the time being, but it requires to look at the history of neural data. So keeping that in mind, we also we cannot simply use, we showed that we cannot simply use feed-forward neural networks, and recurrent neural networks would work a lot better because they have this feedback or this kind of memory embedded in them that will allows us to keep track of temporal dependencies, especially the short-term temporal dependencies. So we started with very simple recurrent neural networks as our decoder. And again, as the first step, we didn't touch the feature engineering part. So we still are using spikes or rate of firing as our features with 50 millisecond beats. But instead of the Kalman filter, we are replacing it first with just the recurrent neural network. And we perform the same kind of open loop phase of center out reaching task. That we have sessions of 3 minutes long, and we already have those recorded data. So we first started with offline test of the algorithms, and then we actually tested these algorithms with patients and human subject in the loop as well. So just to quickly go through this, so we observed that actually recurrent neural networks can work very well to a good degree. We are looking here at the correlation coefficients between the actual movement or the target movement versus the prediction of the algorithm. So as you can see, especially in this patient, because of the location of the electrodes, we are doing very well with the Y position prediction. And we get a correlation coefficient of 0.75, and it does decent with X position. Please keep in mind that this is offline. It means that when we do actual online testing, because there is a visual feedback, the patients actually can correct and the system has the potential of performing even better. We also tested this with LSTM, with a long short-term memory type of neural networks. And again, we saw that the performance is promising. The reason that I'm saying is promising is that in comparison with the Kalman filter, maybe some of you look at this and say, oh, this doesn't look that good, especially for X. But if you look at the Kalman filter, which is the point of reference, you see that these algorithms actually perform a lot better. So this was promising for us. So then we took a further step and we tried to come up with better algorithms rather than just simple recurrent neural networks, especially with the goal of reducing the hardware complexity, reducing the number of weights and nodes needed, as well as reducing the history needed in terms of neural data. So we moved to a dynamic recurrent network. We added an extra derivative state in the system. We also added a feedback to the system. So I'm not going to go through all the details of it. We built a deep multi-state dynamic recurrent network, a neural network, and we basically used the scheduled sampling to solve training and testing discrepancies because we have feedback in the system. And this was again even performing much better. So this is the result for dynamic recurrent neural network for another session. And I have to say, we test this on many days, many sessions. This is not just one day. And we compare it again with the Kalman filter and also linear models. So this was great promise. It had great promise for us, and it was actually presented at NeurIPS 2019 in December. So we showed that this dynamic recurrent network actually performs much better than previous approaches or simple recurrent networks. And it also reduces the hardware complexity by reducing the required history and required number of neurons per layer. So this was promising for us in terms of moving towards hardware implementation. But we are, maybe another thing that I would like to mention is that we've been very interested in making these systems robust. So instead of using, and by robust I mean so that we train it on a number of days, and then hopefully we don't need to retrain and the patient can use the system for many days to come. And we need to train maybe only once in a while. So therefore, for that, we moved now to one step back. So instead of just using spikes and firing rates, we thought about how we can find features that are more stable over time. So basically, instead of using spikes, we look at the raw digitized neural signals, which will include local field potentials, spikes, and all the features across the frequency. And we looked at wavelet scales and frequency bands as our features this time. And again, this is in our paper if you are more interested. And we showed that actually we can achieve better performance in terms of robustness over time. So what's going on here is that we train the network for 20 days using different features. So the neural network either receives the spikes or different frequency bands or different wavelet features. And the red one are the mid-frequency wavelet features that are used for decoder. And as you can see, the correlation coefficient is very good over time when we train on 20 days and then we test on the following days. So then again, this was promising in terms of moving towards more robust neural networks. And where we are today is that we are moving towards hardware implementation of this neural networks on chip. We have done a lot of work in terms of pruning and reducing the weights and some novel techniques that hopefully we will publish very soon. And we are moving towards implementation of the decoder in 65 nanometer technology. So I would like to also thank all the team members for this project as well. Benjamin has been the lead graduate student, and Sahil has been the lead postdoc, and Maitrey was an undergraduate student at Caltech, who is now a PhD student at MIT and did her senior thesis with me. And this has been very close collaboration with Richard Anderson's lab. and he's research scientist. So I also would like to acknowledge all the funding resources. One thing that I have to mention is that we tested our neural networks with patients, and they actually really like it better than Kalman filter because it's a much faster algorithm and the delay in the loop was reduced. So I would like to stop here, but I would be very happy to answer any questions you may have. So I think, should I unmute?
Just like to say thank you. Very inspiring, incredible work. Really loved it. Thanks.
Thank you. Thank you for being here and for inviting me. I would like to thank the faculty who invited me today.
Can I ask a question?
Sure.
I was wondering, so if you use the Kalman filter, but with the design features, like the richer features you described in the end, does that work fine?
Actually, I think we did that. It works better than it spikes, but not as well as the dynamic recurrent neural network. But that's a good question, Mariam. I have to actually go back and look at, because my student tested a lot of different algorithms and a lot of different features. And maybe I have to look back at that to give the most accurate answer. But as far as I remember, he did that. So we had actually, we are doing a lot of studies right now to understand why actually wavelet are performing better over time. We have some hypotheses and we are trying to prove that. But another thing that we are doing, wavelet was our first, again, attempt because it's a well-known feature. Right now, we are actually trying to use a CNN, a convolutional neural network, to actually generate the features for our next stage of decoder. So that's an ongoing work in terms of how to really improve this feature engineering aspect so that we get better robustness over time.
Thank you very much, and very interesting talk. Thanks.
Thank you.
So for the localization system, are you continuing to develop that further? It seems very
Yes, actually for that, we are about to form a company, startup company because the most research part has been done at Caltech. So now we are kind of moving to start a company and do the rest in terms of commercialization in a company.
We have time for a few more questions.
I wasn't sure exactly if I went over time or under time.
No, this was perfect.
So I'll ask a couple of questions. So back to the implantable devices with the communication, the radio. I noticed the size of I was trying to understand the size of the coil. There was one picture where you showed a number of coils stacked up. Obviously, that's the source that you'd have outside the body. But for the implantable coil, roughly how large are those things? And the other question I have is, in these, I do a little bit of work with the radiology group here with radios for positron emission tomography systems, which are increasingly combined with MRI, as you know. So, if you come up with something, it has to exist in, the environment with the MRI. So I kind of wonder about the interference of any type of communication that you might have going with implantable devices, not just for imaging, but also for neural interfaces in general, for anything that you implant in the body. Basically the selectivity requirements of the of the radio? How sensitive is it to interference?
These are great questions. So Chris, let me first show you maybe some of the initial devices. So the first complete wireless device that we built was this glucose sensor. So this is the on-chip antenna. This is about 1.2 millimeter by 1.2 millimeter. And it operates at around 915 megahertz, close to 1 gigahertz. So it's wireless power and backscattering based. But this is not going deep into the body. This is a subcutaneous device. And we made the device very low power. This is a 5 microwatt device. And then for the atoms device, we had a similar kind of design that was this one. So again, it has an on-chip antenna. This one is a little bit bigger, but about the same kind of principle. And it operated in the mice because again, it was a small mice and we could easily perform the power and data telemetry. But going back to the orthopedic surgery where we want to go deeper inside the body. So so in this device, we actually moved to lower frequency. This is about the ISM band that is around 10 megahertz. And the antenna is actually going around the PCB. And this is the size right now. So the size was given, so we worked with an implant company. So the titanium rod is actually quite big and it has many holes in it. So let me see if I can show you another slide that shows the titanium rod and how this sits on top of the titanium rod. So in terms of its size, it wasn't a problem because I don't know if do you see this slide or should I share?
Yeah, I can see.
Do you see the titanium rod?
Yep.
So basically, the size is not a big problem in some of these orthopedic surgeries because we are dealing with big bones and big implants, and we can simply put the device here. And again, the size was also partially because we used an external magnetic sensor in this case. So, so in this case, power delivery was easy because we used this external coil, not an on-chip coil. So that's the first question. Overall, it goes really hand in hand with power consumption, total power consumption. Again, here our power consumption was higher because of this big magnetic sensor. But eventually, if we can have everything on a single chip, we can have a smaller chip, lower power, and maybe again integrate the antenna on chip. But this remains a big challenge. Power delivery inside the body remains a big challenge, and has been really, for us, has
particularly if you try to put the antenna on chip.
Yes.
I mean, then that's going to be, I mean, the antenna efficiency is going to be, that is, so the one that was on the chip, do you know what kind of antenna efficiency you were getting roughly?
Overall I don't remember the exact antenna efficiency but the loss from the transmit to receive, the overall loss was 45 dB, minus 45 dB.
Okay. So
it's very lossy for even a centimeter of tissue. Of course, it depends on the tissue depth. So really, there's a lot of absorption in the tissue, and the antenna is so tiny, so you don't get much power. But at the same time, we are trying to make the chips really, really low power. We made the power management extremely efficient, as efficient as we can. So all of these optimization that at the end, you get to a point that the device can work. But remains a big challenge. I acknowledge that. In terms of your second question, was it more of MRI compatibility or interferences between different devices?
MRI compatibility, but then I extended the question to just generally speaking, interference for implantable devices, in general. Something we might put in the body and interference with the communication.
So again, actually, maybe this fact that the device is like the tissue is so lossy, the device is so small, it helps us actually not to worry too much about interferences, because anyway, it's so you have to get very close to detect the signal. So we haven't seen much of interferences because, again, overall, it's near field proximity, and there are a lot of, the signals are very weak, so they don't interfere with each other. But interference from external devices, at least with the glucose sensor, we didn't have any, because again, we're using the ISM bands, and I'm not sure if that would be eventually a problem if we have many of these devices.
That's what I wonder, actually.
Yeah.
And, even if you look at ISM band, you still have some cell phone bands right around a gigahertz, right? So it's not too far away. And I just wonder if somebody wanders underneath the base station, in the future, if you've got some of these devices, how sensitive is it to that? Yes, you get enormous isolation inside the body.
Right.
But then we're talking about in some cases, we are talking about huge signals. In the case of MRI, it's just, it's the roof.
Right.
I mean, these fields are just enormous. So I think it's an interesting open-ended question at this point.
Exactly. And especially a lot of these devices will not work in MRI. So MRI compatibility is one hand, and whether they would operate while under MRI is, I don't think any of these devices will operate correctly under
unless perhaps if you went way up in frequency. So in the millimeter wave band, right? So the field, so actually this is something we've looked at. Well, okay, I don't want to take away from other people asking questions. That's an offline type discussion.
Sounds good, but definitely it's very interesting. The problem with going to high frequencies, then you get more and more absorption in the tissue. So really,
agreed.
It's gonna kill you, yeah. But these are a lot of open questions left, a lot of technical challenges left in this domain.
Azita, that was a fantastic talk. Thank you. I just had a quick question or point of clarification. Does the orientation of the chip inside the body affect your ability to localize? And are there, can you comment on, if that's the case, can you comment on whether calibration routines are required to remove the ambiguity that may result from orientation, the spatial ambiguity?
Yeah, that's actually a great question. And in the first prototype, we actually had that. So we need to first create a relatively uniform magnetic field to estimate the angles. So we actually, in our published paper, we discuss how we can actually find the direction by first having an extra phase that we will apply a relatively constant magnetic field. Constant in terms of in one direction. But in this particular magnetic field sensor, actually, it gives us a vector. So we actually can measure direction with this commercial magnetic sensor. But it's definitely, it's a great question whether in certain orthopedic surgeries, the orientation, of course, matters as well, not only the XYZ position.
Got you. Yeah, because I was just imagining if the angle varies, then you almost end up with a contour of possible locations for any given readout in 3D. But I see. Okay, I'll follow up with questions on that. That's really interesting.
But that's definitely a good question, and we've been addressing that. As I mentioned in the first paper, we addressed how we can do that with adding one extra phase to the measurement.
Any other questions from the audience?
Hi, yeah, I had a quick question. Great talk. Going back to the neural interfaces work at the end, you made a comment that in using it, testing the algorithms in real time with the patients, that they particularly responded to sort of an reduced latency. And I wasn't entirely clear where that improved latency came from in the algorithm. So I wondered if you could clarify.
Yeah, that's a good question. So overall, it seems that we have a little bit less delay in the system, but also it seems that the algorithm also learns better in terms of translation to kinematics. And because of that, the patient felt, so what we do, we give a questionnaire to the patient after each session that they rank different, like they first test with Kalman, and then they test with RNN, and then with DRNN. So they give us some testing in terms of how it felt and did they feel in control. So it seemed that, so the DRNN actually got the highest ranking because the patient felt a lot more in control. And also he felt that the system responded better to the way that he intended. Again, it's not exactly clear what he meant by it, but he felt that he's more in control. And that's a good question for us also to understand really what it means. But our hypothesis is that because the system is more robust, the patient has this feeling that doesn't need to correct every time that is trying to move, then visually look and then recorrect and recorrect.
Great, thank you.
Yeah, can I ask a quick question?
Of course.
Thanks for the great talk. I had a question about the different neural networks that you have applied for decoding. Have you tried sequence-to-sequence recurrent neural networks? Those seem to be pretty effective in terms of extracting features from the decoder towards the encoder, and like in the combination in between the two.
So to use it right before the decoder?
Yeah, so you would train you would have like an encoding sequence and then decoding sequence, and you would like to reproduce the same sequence. And the connection between encoding and decoding will give you, in many cases, it turns out that it will give preferable features.
Actually, now that you mentioned that, I believe my student read few papers on this and he wanted to try it, but we have not tried that yet.
Okay, yeah, sounds good.
So right now what we are trying to do, now we have shifted a little bit into feature engineering. But that's a great suggestion to look into that as well.
Yeah, we are developing such methods and have seen
for what applications?
Success in terms of unsupervised feature extraction and clustering.
So are you
I can follow up with,
yeah, that would be great. I would love to talk to you more about this because we briefly discussed this with my student and he had seen good papers in this domain, but we haven't yet gotten to that point to try them.
Yeah, and this is an exciting application to try to extract those features.
That would be great. If you send me an email, I see your name actually, but if you send me an email, that would be great.
Sure.
Thank you. So I guess I don't see any other questions. So thank you so much for, again, attending and inviting me. It was really fun. And I hope that I can actually come and visit you next year.
Yeah, we're looking forward to that.
So shall we wrap
Yes.
up?
Yes, I think if that's a wrap, if there are no questions, please, yes, do thank the speaker with your clap icon. It's what we are reduced to in these times, but thank you so much.
Thank you.